Thanks for coming. I'm Sky. In regular old Brickspace, I'm a STEM education grad student, and so part of what I do is get really excited about space, so that other people get really excited about space. It's a pretty cool job. You want to introduce yourself?
I'm Alex. I'm a planetary scientist. I also graduated from space engineering, so I just do space.
They do space a little more officially than I do. So we're here to talk a little bit about parts of space that we think are particularly cool, and to tie some of it into the kinds of things that get thrown around in the book, because Nita, as someone who has a casual interest in astronomy, throws around astronomical terms a little more than casually. And so sometimes it's useful to have like a background for when she's like, oh, it's a spectral type G5. Like, if you don't have a background in astronomy, you're like, cool, it means something to her. That's awesome.
I'm glad she's having fun.
I'm glad she knows what she's talking about, because I don't. So a little bit of that. So I think the plan is I'm talking a little bit about stars, and then Alex is talking about planets.
Yeah.
And then we have a program maybe if we have time.
Yeah.
So can you go to the next slide? Yeah. So also bear with me if this is stuff that you already know. I like to make sure that everybody's on the same page. So generally, when we look at those stars at night, they all appear to be faintly white. Depending on how good your night vision is and where you're looking, you might notice that some of the stars are different colors. For example, we all know that Mars is red. That's not a star, but there are stars in the sky that appear red. So in general, star color maps to temperature the same way that a candle flame does. So if you are looking at a candle flame, the hottest part of the flame is blue. The hottest stars in the sky tend to be blue. Then it's white. It's really hard to see in this picture, and I'm sorry. But white is like the next step down in temperature, and then you get yellow, and the coolest stars are red. And then you get into brown dwarfs, which aren't terribly luminous, and that's a whole other thing. We can talk about them a little more later. So in general, hot stars blue, cold stars red, and the things in between. Our star, for example, is pretty average. We are yellow. We've got a yellow star, spectral type G, but I'll talk a little bit about that later anyway. So yeah. So, can you go to the next one? A little bit about how stars come to be. So, when I was 13, I had heard that stars were giant balls of gas, and I kind of pictured them like constant lanterns. Like they glow eternally somehow, but they don't really change a lot. I went to an astronomy festival in Utah, accidentally. I just kind of ended up there. And I went to, they're like, let's go to a talk. And I was like, sure, okay, I guess. And the park ranger talked about stellar life cycles, and I realized that stars could explode, and I was like, what? Have you been hiding this from me the entire time? So we're talking a little bit about that. Basically, stars are giant burning balls of gas, but they start out as giant floating balls of gas and dust. Less balls, more clouds. So back in So You Want to Be a Wizard, when Fred calls Nita a child, except it's not really a child, it's kind of a nebulous floating cloud of gas and dust. This is a picture of the Orion Nebula. It's a good example of a stellar nursery. It's just a swirling ball of gas. So eventually, within your swirling ball of gas, there are density fluctuations. So there are areas where the gas and dust is closer to each other, and there are more particles per square or per cubic unit of space, basically. And those density instabilities occasionally will then, things will get closer together. And then they'll have more gravity, so they'll attract things more closer together. And you'll just get this big, giant kind of whoosh type of thing happening. Eventually, as that happens, the thing is all spinning around, and then you'll get things like our baby planet pictures! Yay! So this is an example of a protostellar disk. It's in the Orion Nebula, I believe, and these little tracks are baby planets. It's where turned into rocks, are starting to float around and collect things in their path. And so this whole thing is kind of swirling. You've noticed the cloud of gas in the center is enough stuff is falling into it and stuff is getting closer enough together that things are starting to ignite. So basically, in a star, you have a whole bunch of stuff, like a whole bunch of stuff. And it is all squished so closely together that the helium atoms in the center fuse and become, the hydrogen atoms in the center, thank you. The hydrogen atoms in the center fuse and become helium and release a whole bunch of energy. So that's why stars burn. Most stars will spend most of their lives burning hydrogen into helium. Next one, please. Thank you. This is our sun. It's kind of orangey because it's a Soho feed, but yes.
So can a stellar nursery produce multiple stars, and do they kind of like move away from their nursery, or like how does that work?
So can you go back to the Orion Nebula one, actually? Yes. So depending on the nebula, a big nebula like this one, a lot of the reason that we can see it at all, dust is not terribly luminous, thank you, that's the word. Dust is not terribly luminous. So the reason we can see this at all is because there are stars in the neighborhood that are lighting it up, basically. And you will get a bunch of, it's like a neighborhood of stars, basically. And so the older stars will have more complex things in them because as younger stars will have more complex things in them because as they get bigger, let me put this into words. So generally, stars are burning hydrogen into helium. As a star gets older, stuff, depending on how big it is, stuff in its core gets closer and closer together. Some stars kind of stop at the helium, and so like the really old stars in our galaxy are only hydrogen and helium. But then really big stars fuse into other things like carbon and nitrogen and oxygen. And so when they die, there's then carbon and nitrogen and oxygen kind of floating around in the nebula area. And so then the stars that form from those leftovers then are more like complex. There's more things going on in them besides just hydrogen and helium. In a nebula, yeah, there will be like young stars that are still forming. There will be older stars that are burning and just hanging out. You'll sometimes see like stars, like accretion disks will interfere and things like that. So the disk that's rotating and turning into a star will sometimes interact with another existing star. That's one way to get black holes, and it's really cool. But yeah, so they don't like float away and disperse into space often. So if you have a region like this, it's kind of like, you know how they say it takes a village to raise a child? That's the village. There's a whole bunch of stars nearby in various stages in their life cycle.
So it's just unspeakably huge, and that's why.
Oh, it is very, very large, yes. Yeah. Okay. So we got a baby star, we've got our adult star, that's our sun. Our sun is currently burning hydrogen into helium in many millions of years. It will eventually run out of hydrogen in its core, and its shell that is now helium will kind of start to expand, and the center will contract, and we'll get a beautiful planetary nebula and a little tiny white dwarf at the center. Like this. So, I don't know if you understand how big the sun is going to get, though. So here's the sun right now. It's very small. At some point, it will become a red giant. Red giants are giant, like really, really huge. It's really, I don't know. I really like scales in space. They're really exciting. If anybody wants a random paper reference, I definitely have read a paper about the like feasibility of over the timescales of like generations and generations and generations using asteroids to slowly adjust the Earth's orbit so that in 5 million years, when the sun is starting to expand and the habitable zone in the solar system is at 1.5 AU, we will, so half again as far from the sun as we are now, we'll like put Earth there. So if anybody wants a silly science paper reference, I got you. Yes?
Where is the Earth compared to that yellow dot sun?
So in a scale model, honestly, Earth is probably like very, very close to it. And it's so small that you can't even see it. The red giant, this is not a like distance comparison, it's just a size of the like sun now versus a red giant. Like the shell that is burning, remember red means it's cooler. So the cooler part of the star as it expands will literally like be out to the orbit of other planets in the system. Yes.
What orbit about does that equate to? The red giant radius?
I've heard Mars.
Okay, cool.
Don't quote me on it.
Or how many AU? It says Mars is 1.5442.
Yes. Sweet.
So putting Earth where Mars
Yeah,
is.
putting Earth about where Mars is now. So eventually the sun will get really, really big and really, really cool and leave behind pretty clouds in the sky. Like that. So here's our big giant planetary nebula. It's just a shell of gas that's really pretty and made of different stuff, so that's why it's different colors. And the tiny, tiny, tiny little red dot, a white dot in the center, that's a white dwarf. It's a helium star. It's fairly dim and fairly small. When scientists first saw these planetary nebulae in the sky, they thought it was like the remnant of a planet that exploded. We had some interesting ideas when we like first looked up. So that's why it's called a planetary nebula. Yeah. The other option is if the star is way, way bigger than our sun. It means that its core is way, way hotter and things are getting even closer together, which means that you can go beyond fusing hydrogen into helium. You can start fusing helium into carbon and other things like that. Yes, Aaron?
Can I quick comment on planetary nebula?
Yeah.
This is why my professor said that you should start naming things after what they look like rather than what you think caused them, so that when you're inevitably wrong, you have a name that doesn't survive 200 years to confuse everyone that hears it.
That's true. But so, the really, really big stars also make really, really big explosions when they die. And there's like crazy things happening, like there's a double wave bounce. So as gravity brings things closer to the center of the star, right? At some point it starts to, there's like a double shock wave. So like the gas will start to fall in and then it will bounce and like, there's like, you can see it in the like data from supernovas. I'm sorry, I'm now blinking on my technical star terms. But it's really cool. Our sun is not large enough to go supernova in its lifetime. There are a couple different ways to get supernovae. One of them is having a like red giant interacting with another star and like, kind of feeding off of its gas envelope. There are a couple other ways, and it depends on what's around and how big your star is and what's in its immediate locale. But yeah, supernovae are cool. So generally, this is where Juanita talks about like spectral type G and things like that. The spectral types like vaguely correspond with the temperature, the surface temperature of the star. Sorry. And you can see on this spectrum, the surface temperature also corresponds to the color. The hottest, bluest stars are type O. So the star that the planet in Wizards of War, whose name I'm now blanking on, that was a type O star, really blue, really harsh, really not a friendly place to stand near, probably.
It's called SEC.
Huh?
SEC.
SEC. Thank you. But so the order goes O, B, A, F, G, K, M, and then if you're into brown dwarfs, even cooler stars, it goes L, T, Y. So the mnemonic, thank you to my planets professor in undergrad, is O, be a fine girl or guy, or it's one of those things that's regional. The way that I learned it is O, be a fine girl or guy, kiss me, and then if you care about brown dwarfs, it's later tonight. Yes. So there's your spectral type. It's kind of like the planets mnemonic. There are regional variations depending on who you learned it from and where and when. But that's just the one that I know. So this is a Hertzsprung-Russell diagram. It's just a plot of color and temperature versus how bright the stars are. This strip here is the main sequence. So these are hydrogen-burning stars. And then we've got white dwarfs, running out lifetimes. So stars that don't last as long, stars that last a really long time. Yes?
The solar radius and brightness plot look to be logarithmic. Is the surface temperature also log?
Surface temperature is not log.
Okay.
But yes, the brightness and the lines here for the solar radii, these are log, so it means they're in multiples of 10, and, not multiples of 10, like
Powers.
powers of 10. Thank you, that's the word. So if you were to, if you plot with the powers of 10 on the scale, you'll get this nice looking thing. The trends are a lot harder to see if you plot it on a different axis. Talk to me later about axis scaling and data interpretation, but that's not it for now. So yeah, and then I just have some pretty galaxy pictures. The other thing that Nina talks about is like casually tossing out galaxy morphological names. So we live in a spiral galaxy. It just means that it looks like a pinwheel. This is our closest neighbor in space, Andromeda. The other picture that I have is kind of our like prototypical spiral galaxy. It's called the Pinwheel Galaxy, so you can really see there's a bright central core, and then pinwheels coming out of it. You'll notice we tend to get older stars. Bluer stars. So bluer areas are star-forming regions, younger stars. Older stars are towards the center, and there's kind of like a halo around the galaxy. The other type that Nina likes to talk about is barred spiral galaxy, where there's a bar through the center. Those are my particular favorite. They look really cool. And then there are other types. There are elliptical galaxies, which look more like ovals than anything else. There are irregular galaxies, which basically just don't fit into any other categories, because that's how science do. But yeah. Anyway, I talked a ton. Time for Alex to talk more. Do you want to go inside?
This is awesome. Want to play that out?
Yes. So, essentially, an exoplanet is any planet that's not in our own solar system. So that's like all the planets that they go to in Young Wizards. Right here is a little animation of the TRAPPIST-1 system, which they discovered a couple years ago, and it was really exciting because there were like 7 planets, and they're all really close. They're all within 1 AU of the star, if I remember correctly. It was just a very exciting discovery. So yes, here's the definition. There are a ton of exoplanets in our galaxy alone. There are currently about 4,000, I think just over 4,000 confirmed exoplanets. We also have what are called exoplanet candidates, which is where we're like, maybe this is an exoplanet, but we haven't like validated this data yet. We've been discovering exoplanets since dates vary, because of again, the problems with validation and stuff. But here, from 1984 is an actual direct image of a protoplanetary disk, like what Sky was showing, that orange thing that looked kind of like the Eye of Sauron. So yeah, this was discovered in 84 around Beta Pictoris. So that was maybe the first protoplanetary disk that was discovered, but not necessarily an exoplanet. But we've been looking for exoplanets for a while, on Earth first, and then with Hubble, Spitzer, which is an IR telescope. Spitzer also has really fun little videos and animations on its website. And then Kepler, which was the first space telescope actually dedicated to searching for exoplanets. Yeah. TESS is really new and very exciting. We're getting a ton of exoplanetary candidates. I was at a conference last week for technologies in exoplanetary science, and everyone was just like excited about TESS. And then we're coming up. James Webb Space Telescope is maybe gonna be launched.
One of these days?
Yeah, I know, exactly. There's also, but we can also observe from ground-based telescopes. So we've got, big telescopes like the Keck Observatory or the Binocular Telescope Interferometer. Also, just down the street at UDN, Université de Montréal. They're working with the Canada-France-Hawaii telescope, which has an instrument called Spaaaaace. And Spaaaaace is an IR detector that looks for it looks at changing velocities of planets, and I'll get into that more later when I talk about exoplanet detection, which is actually right now. So, planets are very, very small compared to stars, and stars from Earth look very, very small. So how do we even find these planets? There are a number of ways, and I'm going to go into the main four. Basically, so radial velocity is one method. When we say that something orbits around another body, that's not entirely true. It's actually both bodies orbiting around a common center of mass, which sometimes happens to be inside one body. But what this means is that when a planet orbits a star, the star actually wobbles a little bit. And so with the radial velocity method, we can actually detect the red shift and blue shift when the star is moving away or towards us. So what red shift and blue shift are is, if you're familiar with how Doppler works, is like when there's an ambulance going past, the sound is high and then it gets lower. So the same thing happens with light, because light can behave as a wave. And the way that we see it is at different ends of the spectrum. So here, the star is wobbling away from us, so the spectrum is shifted towards the red part. And here the star is wobbling towards us, so the spectrum is shifted towards the blue part of it. And that tells us, okay, the star's not just sitting there, it's being perturbed or moved by a planet going around it.
So that's the only reason that a star would wobble?
There can be other perturbations from other things, nearby stars, or if it's a binary system, for example, or the mass of the center of the galaxy can also add small gravitational perturbations, but the gravitational perturbations due to planets, because they're so much closer, tend to be bigger. So the next method of detection is the transit method, and that's basically, if you're lucky, you get a star and you get the planet and it goes right in front of it. This doesn't always happen, which is why we have to use other methods, but when that happens, you get a nice dip in the light coming from the star, what we call the flux. So this is HD 189733b, which is the canonical exoplanet. Literally, if you studied exoplanets, like, you've probably plotted this light curve. HD 189733b is it's a gas giant, and it orbits its star very, very close, even closer than the orbit of Mercury around our star, which makes it extremely hot, and that's what we call a hot Jupiter, which is a fun name. The third method is direct imaging. So we used to have more of this. It's very difficult because stars are so dang bright. So there are methods to to filter out the light of the star, kind of like when you're looking at the sun and you have to hold up your hand like this. Don't look directly at the sun. So this is the HR 8799 system, which has at least 4 planets, and they are all massive, and that is what allowed them to be directly imaged like this. So as you can see, the star itself is blocked out, and you can see 1, 2, 3, 4. One of them is approximately 5 times the size of Jupiter. The other 3 are approximately 7 times the size of Jupiter. So they are chunky. And the last method that I'm going to talk about is gravitational microlensing, which is a kind of big word, I guess. But basically what that means is that, so Einstein talked about how gravity can bend space-time. And gravity, so what that means is that light is coming like this, and then gravity happens here and light goes, oh, I kind of want to go that way a little bit. So if we look at a very distant star, we see the light coming towards us from it, like this. But then if there's a star in front of it, the light might go, oh, I want to go that way a little bit. And if the star has a planet, so I'm our star, our more distant star. There's another star here, it's coming like this, the light is going boop, 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 oh, I want to go this way a bit, but then there's also a planet, and it's gonna go, the planet is also going to perturb the path of the light, and that's where we get this tiny blip. We have the effect of the star that's constant, but the planet around the star will cause little blips in the data like that.
So would gravitational microlensing allow us to know that it exists so that we can use one of the other forms of detection to specify what type it is?
Yeah, potentially. I mean, you can also,
I was just thinking we'd be able to get as much data from gravitational microlensing.
well, yeah, you are able to tell based on the magnitude of the blip, how information about, say, mass, for example. Yeah, you do have to sometimes use a combination to get, for example, light curve is very good for getting information about the radius, but not necessarily the mass of the star. Gravitational microlensing would be better at getting mass information because gravity is proportional to mass. No worries. So I'm also going to touch a bit on habitable planets, which mean planets that we think are capable of potentially supporting life based on what we know about our planet. Because right now we only have one kind of data unit about how life likes to be, which, as anyone who's done science knows, isn't great.
Yeah.
But planets that could maybe support life, we say, are in the habitable zone, or sometimes known as the Goldilocks zone. So Kepler 452b was the first Earth, well, it's a super Earth, but rocky planet detected within the habitable zone of a star like our sun. And we found nearly 20 planets within what we call the conservative habitable zone. That doesn't mean Stephen Harper lives there. Canadian joke. It just there's like a optimistic habitable zone and a conservative habitable zone, essentially. And that's determined by how hot the star is, how big it is. So that can move with the star. It's not like 180 is always the habitable zone, for example. That's all I have to say on exoplanets. Cool.
Okay, so roadmap. I think we can take questions about the first two things, but then we also have this other cool program that is really cool, and I want to show it to you. And we can go on a tour of the night sky or the solar system or whatever. So, are there questions on the first part? Caitlin.
Do scientists actually use the term class and planet like in Star Trek? Because I've seen that. And I'm not sure if that's something that people actually do.
I think that's just a Star Trek thing.
Good.
As far as I know, in Star Trek, the classifications have to do with like how good it is at supporting life, which we can just be like, oh, this is a rocky planet in the habitable zone, but we can't really be like, oh, this has like oxygen, nitrogen, atmosphere, blah blah blah.
Okay, it's good. News outlets are wrong.
Like, they often are.
Yes.
From what I remember looking at astronomy books and whatnot from middle school, I remember a white dwarf being a theoretical thing. Is that, like, we haven't actually, not a white dwarf, a white hole?
Yeah, so it's a thing that we like, I believe, yeah, it's basically a theoretical thing.
Yeah, okay.
Black holes used to be theoretical.
That's
So
true.
maybe
Yeah,
that's
no, so I'm
something
not
that
saying
makes
that
it
like,
less cool.
I'm not saying that it's outside of the realm of possibility or like totally definitively doesn't exist. At this point, it's beyond our ability to detect.
That's fair, absolutely.
Diplomatic.
humanity-wise, like what it means to know something
Absolutely.
scientifically, and
Yeah.
it totally means something different than like layman speak to what it means to know something. Basically, like science. If we say we know something in science, it means that we're pretty sure we kind of have an understanding, but really we are 100% capable of being utterly wrong and finding something that like totally disrupts like what we call our knowledge at the time, which I think is really cool, but it also like weirds a lot of people out because traditionally in K-12 education, we spend a lot of time being told science is fact, which means that when you read a thing in a science textbook, it is true. The end. Yes.
I read an article last week that apparently spiral galaxies do in fact wind up over millions of years. I think Philip Plate wrote it.
That is something that I don't know.
Can I comment on that if you want?
Yes,
I mean, so I haven't read the article, so maybe that's a new thing. But as far as I know, like we spent a lot of time trying to understand the ways in which spiral galaxies could rotate without winding up, because the amount of time that they've existed, they should have wound up like that. But I think the way that the arms are now understood is mostly as regions of density that matter like rotates through. Like that pattern itself is like in the same place, and the matter rotates through it and gets denser, and then rotates out, and that's what forms the arms, and that's what keeps them from winding up, because they're just going through areas that are like nice. That makes any sense.
Yeah.
Yeah, they're compressed and then they come apart, kind of like a slinky.
Well, I think we also need to take into account that a lot of the spiral or barred or ones that have a central mass have a supermassive black hole at the center, which stays at its gravity, being the largest gravitational force in the area to keep it more stationary, or at least in its orbit where it is in the universe, because the galaxies are orbiting also.
I might throw up a picture in the Space Channel of the Slack later, or an animation rather, but there's also interactions between galaxies. For example, our Milky Way and Andromeda galaxies are coming together, and when they interact, they'll essentially unwind each other, for lack of a better term, because of essentially the gravitational effects of them crashing into each other. It's a really cool animation.
Some of the really cool ones, you get things called like tadpole galaxies, where like the core is still there, but it has a really long like tail happening. Those are usually from interactions. Aaron is another
Yeah, sorry, I want to see one more
space science folk.
Space facts. So we did this math actually with some of the kids at the astronomy camp I was at last week. But when you talk about the collision of the Milky Way and Andromeda galaxies, the actual statistical likelihood of anything in those galaxies actually colliding with each other, like two stars or something like that, is very, very, very low. So like the animations that show how they're torn apart, that's all from gravity. It's not from anything.
Yes.
The number of things that will actually crash into each other is very.
Space is big.
Yes. So we have a couple minutes, maybe. I have this sweet program called Stellarium, which is a free program that you can download, and it is basically a night sky simulator. So there are a couple neat things about it. One is you can pick your location. Your location can be wherever you happen to be on Earth at any given time. You can pick the time too. It can also be wherever you really want it to be. I'll show you in a minute a couple different cool options about that. But yeah, so when we were talking about different colors of stars, for example, this guy, Betelgeuse. Sorry, what I've done also is we are looking at the sky as it appears from, I think, approximately here. It tends to pick my location. At this time, but I have handily turned off the atmosphere so that we can see the stars. The other thing that's really neat is you can also, I have the ground happening here. You can change what that looks like depending on what kind of horizon you want. You can also just turn it off and be like, I don't care. We don't need a ground right now. But this, at least for my purposes, helps orient me. So we're going to stick with it. So here's our sun. Here are several planets that I'm pointing out. This is Mercury and Mars. and Venus. These guys will all be pretty close to the sun in the sky at any given time. That's why Venus is our morning or our evening star, because it's close enough to the sun that it's basically daylight whenever you can see it. And then Betelgeuse. It looks like Beetlejuice. I feel like it looks like a sneeze, but it's pronounced as Betelgeuse. It's a star in the constellation Orion, the Hunter. Betelgeuse is a red giant. It looks pretty red. So if I go to the other side of the sky, which means I probably need to turn off the ground, or slash if I go to the search function and find Antares. Sorry, we're going to take a detour to my favorite star name ever. See, we've turned off the ground. Okay. So I'm also going to help orient you, turn on constellation labels. They were lines. You can also have it display art. It looks really cool. Yeah. But anyway, so if you've heard of the constellation Scorpio, it looks kind of like a fishhook in the sky. This is not the way that I usually see it drawn, but it does this kind of like backwards J thing. Oh no, that's a forwards J. I know how the alphabet works. It does this kind of J thing. So here's the stinger on the scorpion. This is the constellation Libra, the scales. It actually used to be considered part of the scorpion's claws. Yeah. But so Antares is another red giant. Its name literally means not Mars, because it hangs out in the same part of the sky as another red object, Mars. And so astronomers, like ancient astronomers, used to be confused by this sometimes, and would be like, "Whoa, what's happening with this red thing? It's not Mars." So Antares. The other interesting thing is, a lot of the, I will couch this in a lot of what we think of as the Western constellations. So Scorpio and the Big Dipper and things like that are actually the way that we map the sky when we're talking about where in the sky things are. If we're looking at a map of the world, we divide it into countries and states and things like that. If we're looking at a map of the sky, we divide it into constellations. Because there are relatively fixed backgrounds aside from the stuff that's within our own solar system. And so you can say that, oh, this cluster is in the constellation Cancer, because you can look towards the area of the sky where Cancer the Crab is, you will find this nebula that you're talking about. Yeah.
That's also how we get the names of meteor showers. For example, the Perseids come from Perseus. The Geminis come from Gemini.
The Ophiuchids.
Yeah.
This thing, this program will also show you the what's that called? The place where it looks like it comes from, the radiant?
Yeah.
The radiant, the place where the meteor shower looks like it comes from. You can set it to show that to you, which is pretty cool. Let's take a brief look at a couple planets, because we can. So let's look at, actually, sun. We have to go to the sun first. Well, actually, no, let's look at the moon first, because we don't need to see all of that. Moon. Here's the moon. I'm going to zoom in a whole bunch, hopefully. Nope, in, not out. Here's the moon. Yay. It's got really great craters. Really great craters. If you ever have access to a telescope,
Hell, just binoculars.
or binoculars, yes, yeah. If you have access to some sort of visual enhancement aid for the night sky, the best time to look at the moon is when it is a partial moon, because then you'll get really great, you'll get really deep, awesome shadows in the craters at the terminus. The edge where the dark meets the light on a partial moon is called the terminus. Yeah. So there's our moon. Our lovely young lizards spend a lot of time upon it. I want to look at Mars, but I don't want to look at it the way that it looks from Earth. So we're going to go to the sun first. And we are zoomed in a bunch. Look at that. It has sunspots. I love this program. It's so cute. Now I'm going to say that I want to view from here, and I have to remember the shortcut key from it. Settings? No. I think it, yeah. Location. View from Sun, where you at? So the reason that I'm trying to view things from the sun is so that when we look at it, it will be fully illuminated. So we'll see the entire face of the planet rather than just part of it. Yeah, it'll stop freaking out in a minute. I'm sorry. It really doesn't. It like automatically turns the ground on when you go to a new place, and it just doesn't know. Oh, I also have to stop time. So time was advancing at a normal moment, and the sky was rotating as the sky tends to do. That's why you suddenly got like crazy spinning happening in the stars. Okay, so we've stopped time. Awesome. We're gonna find the Mars.
The Mars.
Okay, we're gonna close this window because I don't need it right this second. And we're gonna remember how to zoom in. Here's Mars. The thing that I really especially appreciate about the Martian one is that you can click on a place on Mars and it will be like, here's what that crater is. So we're looking at the crater Nardo. Or we're looking at the Teneus Cavus. I'm sorry, I don't speak Latin. I can like hear Sarah from like 3 rooms over just going, ah! Oh no! Sorry! But so, here's Mars, the other place where I find to spend a lot of time. In our last like 2 seconds. I want to show you my favorite update that they've done is we have gotten the New Horizons data, which means that if you tell it that you want to stand on the map that shows up is from the New Horizons data. So it has the little heart-shaped thing. It's super duper cute. Yeah, Delirium is awesome.
We are not sponsored by
We are not.